All right, I have shared my screen and my mic is on. I hope both are working fine. Somebody could please confirm. All right. Okay, thank you. Um, so first an announcement. I have uploaded problem set 2. I uploaded it yesterday. We will discuss some of those problems tomorrow in the tutorial. In fact, I remember we have one remaining problem from tutorial set 1. So we will first take that and then we will see how much we can cover from set 2. All right, so towards the end of the last class, I defined a fluid element. Uh, First, you need to pay attention that a fluid element is different from a fluid particle. They are two different entities. Fluid particle definition we have already seen. We are now familiar with that. What is a fluid element? Fluid. So far we studied about a fluid particle, which is the smallest entity in continuum description. While the concept of this I'm just reviewing. I covered this in the last lecture also. And just to have a continuation, I am reading what I had on the last slide. So the concept of a fluid particle is useful in understanding the translational aspects of fluid motion. However, it is not adequate to examine other aspects like rotation and distortion or deformation, rotation or deformation. Thus, we now introduce the idea of a fluid element. A fluid element is a small piece of fluid comprising of numerous fluid particles. The size of Fe is small but finite. Okay, here I am showing a uh, fluid element or Fe, and I am using a Cartesian coordinate system. My working coordinate system is Cartesian, and this is what can be called as a fluid element. So it is a cuboid of dimension delta x1 along E1 axis, delta x2 along E2 axis, and delta x3 along E3 axis. And this fluid element I am identifying at time t, and the faces of these of this fluid element. Of course, there are 6 faces of this fluid element. So faces are, there are 2 faces which are perpendicular to E1 unit vector, 2 faces are perpendicular to E2, and 2 faces perpendicular to E3. All right, and of course delta x1 is the length of that, those is the length of those edges which are parallel to E1. X2 is the length of those edges which are parallel to X2, and X3 is the length of those edges which are parallel to the third axis. Okay. I also mentioned in the last class that if you go back in absolute terms, a fluid particle has dimension 10 to minus 4. So fluid element, I will take at least 10 times that size. Okay, so that I have numerous fluid particles inside it. So in that way, I would say the dimension of delta x1, delta x2, delta x3 are of the order of magnitude 10 to minus 3 meter. They don't have to be identical, but they should be of order of 1 mm, 2 mm, like that. Okay, now fluid element has the same set of fluid particles at all times. So that is part of the definition. So at time t, you identify all the fluid particles that are associated with this fluid element. And at a later time, if I am tracking what happens to this fluid element, I will be focusing only on those fluid particles which were originally part of the fluid element. All right. What are the specific questions we are interested in addressing? We actually want to find expressions for rate at which this fluid element is rotating and rate at which its edges are changing their lengths. And we will look at fractional change, or what fraction the length, which is right now delta x1, by what fraction it changes with time. That's the kind of question we want to find. That's the kind of quantity we want to find expression for. And finally, rate at which the volume of the fluid element is changing. Clearly, right now the volume is delta x1 times delta x2 times delta x3. But at what rate is it changing at this instant? All right. So these are the questions which we will try to address in today's class. So we start the derivation for these quantities. So as I said, my working coordinate system is Cartesian with the origin at O. This is a reference frame with respect to which the motion of the fluid is being observed. Now, I have chosen, I am writing the position vector of vertex A as X. Okay, so this can be thought of as the base location. So X has coordinates x1, x2, and x3. Now using this x1, x2, and x3, you will see that very soon I will write coordinates of all other points, knowing that the edges are delta x1, delta x2, and delta x3. So for you will see we will have Taylor series expansion also. So for Taylor series expansion, we will use this location of A as the base location. So I am naming all the vertices here: A, B, C, D, A, B, C, D, and then E, F, G, H. These are the 6 vertices. And as I said before, all faces are normal to E1 or E2 or E3 at time t when I am starting this derivation. Now, for simplicity, to keep the algebraic complications less during this class, I will assume that the velocity field that is existing, it is number one, 2 componential, which means that it does not have a V3 component. And I'm also assuming that it is 2-dimensional. So you see I have written only x1 and x2 as independent variables. Now this assumption is not required to actually derive the full expressions. I mean the expressions that we will finally look at, they will be applicable for 3-componential 3-dimensional flow field. But starting with the 3-componential 3-dimensional flow field will increase the algebra a whole lot, and I have a suspicion you will find it hard to first handle the algebra and also get insight whatever we can. I mean, you will find it difficult to get physical insights. So we will derive it first with these assumptions, 2-componential and 2-dimensional in the class, and then whatever expressions we arrive at, we will recognize the pattern and extrapolate that for a 3-dimensional case, which holds true for, I mean, we will not just extrapolate and what I'm assuring you that the expressions that we will get after extrapolation, that holds good, and that can also be derived with some extra effort, but we will not do that in the class. What we will do is only derivation for 2-componential and 2-dimensional. All right. So as I said, we are interested in deriving expression for at what rate, and when I'm saying rate, I mean time rate. With time, at what rate length of AB changes. You see here AB, length of AD changes, and rate at which AB and rate at which edge AB rotates relative to E1 axis. Now, mind you, these E1, E2, E3, they are frame embedded unit vectors. So with time, they themselves do not change. They are always fixed as seen by the observer. So I would like to know at what rate the edge AB is rotating relative to E1 axis. And then I would also like to know at what rate edge AD rotates relative to E2 axis. And with that, we will try to derive an expression for a measure of at what rate the entire fluid element is rotating. And finally, as I said before, volume of the fluid, what rate volume of the fluid element changes. Now, we have to realize this, that since there is a velocity field existing, uh, when you go from time t to time t plus delta t, when you go from time t to t plus delta t, all these vertices, which are essentially fluid particles and part of the fluid element, all these vertices individually will translate, right? Going from t to delta t. Why will they translate? Because there is a velocity field existing everywhere. So point A will translate by velocity vector that exists at point A, right, at this time, multiplied by delta t. And similarly, point B will translate and go to a new place, and that translation will be governed by whatever is the velocity of B at this instant multiplied by delta t, and so on, right? So it is the velocity field that will force all these fluid particles, which are part of the fluid element, to translate according to the velocity field. And because of that, the cuboid, right now what is a cuboid, may not remain a cuboid at t plus delta t, right? That is the idea. Now, the way I have taken the velocity field, that there is no third component, there is no V3 component. So I hope you will agree with me that A and B and C and D, they will not leave their original plane, right? Because there is no V3. There is, so A, B, C, and D, they are lying in a plane which is parallel to E1 and E2, X1 E1 and X2 E2 plane. X1 E1, X2 E2 is a plane, and A, B, C, D are at time t lying in that plane. Since there is no third component of velocity, at time t plus delta t also, they will remain in the same plane. There is nothing, there is no V3 that can force them out, right? So that thing we realize. And actually same argument implies to each cross section of the fluid element. I mean, this fluid element is a cuboid. So what argument I presented to convince you that ABCD will remain in the same plane at t plus delta t, that is true for any cross section of the fluid element, not only the cross section containing ABCD, that is true for any cross section of the fluid element which is originally parallel to X1 E1 and X2 E2, right? So thus it is sufficient to examine what happens to vertices ABCD. So whatever happens to ABCD will happen in the plane, same plane, and whatever distortion you see in the fluid element, that will be identical to corresponding fluid particles. That distortion for that movement of ABCD will be identical to the corresponding displacement of fluid particles happening in other E3 planes. Okay, or sorry, in other planes, but parallel to X1 E1, X2 E2. Okay, so at time t, this is the situation. ABCD is there, and it is a rectangle with delta x1 and delta x2 dimension. Now at t plus delta t, as I said, every point of this cross section will translate according to its local velocity vector. So at t plus delta t, this will be the general picture, what I'm showing here. A has displaced from its original position to a new location, which is still I'm calling A. So A, B, C, D, mind you, they are labels for fluid particles, and that's why I'm not changing those labels. A was here initially, and A has now come here. Now B might have gone here, C might have gone here, and D might have gone here. So it kind of becomes a rhombus at t plus delta t, right? And I'm denoting this angle that AB is subtending at t plus delta t relative to E1 axis as delta alpha. And this angle that edge AD is having with E2 axis at t plus delta t as delta beta. All right. So this is a kind of general deformation we are expecting. Now, coordinates of AB and CD at time t were what I have shown here in black labels, in black fonts. So as I said, A is my base location. So at time t, it had coordinates x1, x2, x3. And then B, C, and D will have these coordinates. I will let you stare at it and see that I have written it correctly. So mind you, AB is delta x1. So that's why coordinates of first coordinate of B is x1 plus delta x1. But then at time t, AB is along even axis, so x2 and x3 remain the same. If you go to C, it is x1 plus delta x1, x2 plus delta x2, and x3, and D is x1, comma x2 plus delta x2, comma x3. Right? And see, all of them have, of course, we chose them on a plane. So the third coordinate is identical, whatever it is, x3. So this is at time t. Now, the new coordinates of fluid particles A, B, C, D at t plus delta t will be governed by, as I said, by the local velocity vectors of fluid particles A, B, C, D at time t, and their new locations at time t plus delta t will be, if I call use a general symbol, representative symbol x prime, the new coordinate of a fluid particle will be its original coordinate plus velocity that existed where the fluid particle was at time t multiplied by delta t. Right? So we will use this idea now to write down the coordinates of A, B, C, and D at time t plus delta t. That's our next task. I want to remind all the students that it's good that you are listening to my lecture, and it will be good when you read the notes, but things will still not be good enough unless you, after reading it, you derive things yourself and make sure you are able to get to the same expressions that we are getting in the class. As I said earlier, unless you derive, you get a feeling that sometimes you get a false sense of understanding that you have followed everything. But when you start actually deriving with a pen and paper, you start having problems, and that is the time to get doubts clarified and take your understanding to a deeper level. So do not miss that step as far as this course is concerned. Okay, so this is what I'm going to do, right? Find the new coordinates, and again, we need Taylor series. As I said many times in this course, we will invoke Taylor series, and first order will be, we will use first order approximation. For example, if phi is the dependent variable and dependent on x1, x2, then you remember that you may remember that we can write phi in the neighborhood of my base location, which is x1, x2, as this. So there are two partial derivatives involved, and delta x1 and delta x2. And again, the partial derivatives are at the base location. Okay, so I'm going to use this idea and first write the velocity vector, or the three components. Rather, I'm not writing the third component because it is, I've said that it is a two componential velocity field. So V3 is 0. So I am writing 1 and 2 coordinates of the velocity vector that exist at A, B, and C, D at time t. Remember, we need velocity information only at time t. So this is what I have written here. Please pay attention to this, and I will again let you stare at it, look at it for some time, and see that all the expressions that I have put in black within black boxes they have been derived using a Taylor series expansion like this, using A as the base location. And I hope I have not made any mistakes. If I have, then you can point it out now, or later if you find it, you may please let me know. Okay, so what we are doing here, velocity at A is v1, v2, that is the base value. P, if I want to write expression for velocity at B, using the base value v1, v2, what will the components be? The first component will be v1, which is the value at base location A, plus del v1 del x1 multiplied by delta x1. Why is this coming? Because B is displaced from A at time t by displaced by delta x1 in even direction only. So you have del v1 del x1 delta x1. Similarly, v2, the second component of velocity at B is v2 plus del v2 del x1 delta x1. Okay. If I go to location D is displaced from A at time t by a distance delta x2 only in E2 direction, and that's why the first component of velocity at D can be written as v1 plus del v1 del x2 multiplied by del x2 delta x2, and the second component will be v2 plus del v2 del x2 multiplied by delta x2. So both B and D have only single displacement only along single axis, either along E1 or E2. But then fluid particle C at time t had displacement with respect to, or measured from A, both along E1 and E2, x1 plus delta x1 plus x2 plus delta x2. So the full expression for their velocity components will have both the derivatives sitting there. First component is v1 del x1 delta x1 plus del v1 del x2 delta x2, and second component is v2 plus del v2 del x1 delta x1 plus del v2 del x2 delta x2. I hope it makes sense. So I hope you will appreciate why I didn't include the third component. That would have been nice to keep the derivation very general from the beginning itself, but you see I am already running out of space and it is becoming quite busy. The slide is becoming quite busy. All right, so these are the velocity components existing at the locations where fluid particles A, B, C, D are at time t. Any question? It was dependent on this. You are right. If V was dependent on X3 component 2 and didn't have a component T3, then every cross section will not behave like ABCD. You are very right, Amitesh. Yes. So if I want to derive with this, in this general case, I will have to consider those components also. Any other? Any other question? All right, so if not, then I will proceed. So once we have these velocity vectors, components of these velocity vectors, now what I have to do, if I have to go to each fluid particle, take the velocity component, multiply it by delta t, and add the original coordinates of that fluid particle, and that will become the new coordinate. That will become the new coordinates of ABCD at time t plus delta t, right? That's what I'm doing here. Well, here I have, that's what I'm doing here. So the new coordinates, that is at time t plus delta t. So here I made a picture in another way, again to convey with the hope that you are able to visualize what's happening. So this is the coordinate system at time t. We had A, B, C, D, and these purple arrows, what I have shown, I'm trying to say that they are all getting displaced over time delta t by their local, uh, measured by their local velocity vectors, right? And that's why in general, they will be displaced by different amounts, and that's why a rectangle doesn't remain a rectangle in general. So the new coordinates of A are x1 plus v1 delta t and x2 plus v2 delta t. And I'm getting it from here. You see A has velocity v1 and v2 at time t. So I just multiplied by delta t, and the new coordinates become original location, original x1 plus v1 delta t, original x2 plus v2 delta t. B will become original x1, which was x1 plus delta x1, that was its original location, plus the velocity vector, one component of the velocity vector of point B at time t multiplied by delta t. That is one location. The second location, original location for the second coordinate, the original location was just x2, and then we add whatever we have here for B, we multiply it by delta t, and so on. Again, I will leave this slide for a few seconds for you to grasp this idea. So here the expressions are becoming complicated mainly because of partial derivatives, and partial derivatives are also the reasons why we may make some mistakes. So where it should be v1, where it should be x1, they are all to be carefully put based on what they actually mean, or what we are actually trying to get from this. All right, so I hope you have gotten some idea how the coordinates of A, B, and C, D are arrived at time t plus delta t. And again, I am not expecting you to grasp everything. 40–50% you are able to grasp, that's good. Rest of the details, while you read and derive, I hope things will fall at right places. Okay, so now continuing here. So this is the situation. Same figure I have drawn again for continuation. Now note that Fe is small. Delta x1, delta x2, delta x3 are all small. The significance of this approximation is, or significance of this assumption is, to approximate various expressions up to the first order term of Taylor series. If you do not assume delta x1, delta x2, delta x3 to be small, then Taylor series, if you truncate at the first term or the second term, will not be an accurate representation. If deltas are not small, then the later terms may also become important. And that's why I said that a fluid element has small dimensions. All right, so we have found the coordinates. Now, using those coordinates at time t plus delta t, now let's start writing some trigonometric expressions. So, as I said, I defined this angle as delta alpha, side AB now inclined to E1 as delta alpha. I can write tan delta alpha. As two coordinate. By two coordinate, I mean the second coordinate. Okay, and by one coordinate, I mean the first coordinate. Two coordinate of B minus two coordinate of A divided by one coordinate of B minus one coordinate of A. And this is all at t plus delta t. So focus on this figure alone. That should be tan delta alpha, right? 2 coordinate of B, 2 coordinate of A divided by 1 coordinate of B minus 1 coordinate of A. This is how we find a slope of a straight line, right? That's what I have written. Now, since delta t is also small, in fact, very soon we are going to take the limit when delta t goes to 0. That's how you find rate of change in calculus, right? So delta t is already small. We expect delta alpha also to be small. Because I can always argue I can make delta t arbitrarily small so that the displacement or distortion of ABCD from its original form can always be taken to infinitesimal values. In that case, delta alpha can be written as approximately tan or tan delta alpha can be written approximately as alpha. So this quantity what I had left hand side, I can say it is delta alpha itself. Okay, so now I'm essentially writing expression for delta alpha. And then this 2 coordinate of B, 2 coordinate of A, 1 coordinate of B and 1 coordinate of A, I have taken from the previous slide and put them here. Okay. And you see that a lot of terms cancel out. And when you simplify, you are left with delta alpha being approximately equal to what I have here. Del V2 del X1 delta T divided by 1 plus del V1 del X1 delta T. And as I said, very soon we will take the limit delta T going to 0, and we will see what happens to this expression. In fact, I will take delta T on the left hand side first because I want to find rate of change of alpha. We will see that. Let's not jump steps here. I should not have jump steps. So delta alpha is this. Similarly, delta beta, which is approximately tan delta beta, can be written like this. So again, when I say 1 of D, it means 1 coordinate of D, 1 of A, 1 coordinate of A, and similarly 2 of D and 2 of A. So at T plus delta T, I can write tan delta beta the way I have drawn here to be like this. Okay. So again, I will borrow these coordinates from my previous slide here. I will borrow these coordinates from the previous slide, and when I place them at the right places, this is what you get. And again, when you simplify, some terms cancel out. You are left with delta beta being del V1 del X2 delta T 1 plus del V2 del X2 delta T. So see, a pattern is already emerging. Here we had del V2 del X1. Here we have del V1 del X2 in the numerator. Denominator, I had del V1 plus del V1 del X1 delta T. Here I have 1 plus del V2 del X2 delta T. Okay, I'll leave it for a few seconds. All right, here I have written a comment that actually following the procedure that we had on the last slide and on this slide, left side of this slide, you can actually show that just like AB, CD will also have the same angle. I mean, the angle that CD is making with even axis at T plus delta T will also turn out to be the same what we found earlier. So it means that CD will also be inclined on even axis at an angle delta alpha. And similarly, you can show side BC will also be aligned like AD at delta beta angle to the E2 axis. This you can show. I'm not showing everything here, but if you take the coordinates, it will turn out to be. So effectively, we are saying that this what we had as a rectangle in the beginning, now it has become a parallelogram. So it has become distorted. The angles are no more 90 degrees. and the sides are no more the same. They have changed their lengths, but it is still a parallelogram. All right. Even though this part, what I just highlighted, it's really not required for the derivation we are making. It is a kind of a side note. Now we measure the rate at which two edges AB and AD are collapsing towards each other. So now using this expressions delta alpha and delta beta, I am raising, or I'm inquiring about inquiring for a new physical quantity, or expression for a new physical quantity. What is that quantity? I want to know rate at which these two edges AB and AD are collapsing towards each other, right? So initially they were at 90 degrees, and if the body would have been rigid like APL 100, they would have also always remained at 90 degrees. But since fluid is not rigid, it deforms. So the AB and AD tend to collapse towards each other, right? That's what is being seen even in this freehand sketch. They are collapsing towards each other. What is the rate at which they are collapsing towards each other in radian per second? So that will be limiting value of delta t going to 0, delta alpha plus delta beta by delta t, right? The way I have drawn delta alpha and delta beta, we should add both the terms, divide by delta t, and that should tell me how fast AB and AD are tend to fall towards each other, collapse towards each other. Okay. And now that we have expressions for delta alpha and delta beta from this slide and what I had on the previous slide, I can plug things in and then take the limit, right? And see, I put delta t because I want to find rate of change. So this delta t in the numerator gets cancelled out for both the terms. And then whatever is left at the bottom in the limit delta t going to 0, that second term in the denominator will go to 0. So effectively in the denominator, you'll be left with 1. So I have this expression for the question that I asked, the rate at which edges AB and AD collapse towards each other. The expression is del V2 del X1 plus del V1 del X2. And again, reminding you, all derivatives are at location A. Okay. So this is the rate at which they are collapsing towards each other. Now let us measure the rate, or the rate at which the fluid element is rotating. Okay. So what I just the quantity that I looked at, that is not rate of rotation. That is what I just said, rate at which two edges collapse towards each other. But now I'm asking a different question. Measure how fast the fluid element is rotating. Okay. So had A, B, C, D, E, F, G, H been a rigid body, I hope you will agree with me. Maybe you have realized it by this time. Maybe by this time you already are aware of this, or maybe you are not aware. If you are not aware, I hope you will agree with me that if this had been a rigid body, then d alpha dt should have been minus d beta dt. Okay, where alpha and beta would be the angles between side AB and even axis and side AD and the E2 axis respectively. And mind you, I have used a new symbol here, d alpha dt and d beta dt, but they mean this, what I have written in black box here. D alpha dt is nothing but limiting value of delta t going to 0, delta alpha by delta t. So I hope this you accept this statement that if the body was rigid, first of all, delta alpha and delta beta must have a negative sign. They can't collapse. They have to move in the same direction. I mean, the way I have drawn delta beta should be minus delta alpha. And in the limit delta t, this should be the same. And mind you, that is precisely what is called the angular velocity of a body. This would be called the angular velocity of this rigid body with respect to the ground frame, whatever frame we have in context, the third component of it. Of course, it is a vector, angular velocity is a vector, but the third component will be defined precisely like this, d alpha dt or minus d beta dt. Also, again, it is essentially an APL 100 concept, but some of you might not have realized it. I want to first inform you about this. For a rigid body, rate of change in orientation of any arbitrarily chosen line segment is always the same. You take any line segment on a rigid body, the rate at which it changes orientation with respect to even axis will be identical whether you choose AB or AD. That is what actually is represented by this statement. However, for a deformable body in general, there is no guarantee that the rate of change in orientation of different line segments will be the same. In general, they will be different. And this is what I have taken from the very beginning in today's class. AB, I am saying that in time delta t, it gets angularly, displaced angle wise by delta alpha. But AD, I gave it a new symbol, delta beta. So for a deformable body, different line segments can change their orientation by different angles over the same time instant. And that's why they are deformable. Okay. So thus, strictly speaking, we really cannot define a unique angular velocity or rate of rotation for a non-rigid fluid element. There is no unique way to define rate of rotation for this deformable body, because every line segment rotates at a different rate. However, it is customary by convention. We define what is called the averaged angular velocity of a fluid element, and I will use this symbol, omega vector. Okay, we define what is called the averaged angular velocity of a fluid element. And what is that angular average velocity? The third component, which right now we are working with, and which is the only non-trivial component right now for our case. We define the third component of averaged angular velocity as what I have shown here, d alpha dt minus d beta dt divided by 1 by 2. Okay, using segments AB and AD. So now, like, we are making an agreement among all the fluid dynamic community that yes, we realize that the fluid element does not have a unique angular velocity, but still let's define an averaged angular velocity in this fashion for a fluid element. And this definition does give us a sense of how fast a fluid element is rotating. It gives us a sense. Okay. So it may happen that in some types of fluid motion, you will find that even though you start with d alpha dt, you start with the assumption that d alpha dt and d beta dt may be different, but the flow field may be of such a unique nature that it will turn out that d alpha dt is actually equal to minus d beta dt, right? And in that case, this will become what? Or if I say the other way, d beta dt is minus of d alpha dt. So in that case, this will just become d alpha dt plus d alpha dt by half, and that will become finally d alpha dt. So there are cases in the there are some special cases in which you will find that every segment of the fluid element is indeed having same rate of rotation, and we do use this word that in this particular case the fluid is, or the fluid element is having motion like rigid body. Every line segment rotates by the same rate. That is not general. As I said, in general we will keep this expression, and thus the average angular velocity. Now if I use this expression what I got on the last slide, this delta alpha, delta beta, and delta alpha, if you plug these in, this newly defined quantity omega 3 turns out to be this del v2 del x1 minus del v1 del x2. And now you can clearly see the special case about which I was the special case what I mentioned earlier will be true when del v1 del x2 is minus del v2 del x1. In that case, at least at that instant, you can say that the body is having a rigid body motion. Okay. But this example aside, that is not a primary agenda item. I want you to realize that this is how, what I want you to realize at least is that This is how average angular velocity is defined for a general fluid motion. And this is how it is defined. I mean, this d alpha dt minus d beta dt by 2. And using the expressions that we derived earlier for these d alpha dt, d beta dt, it can be written in this manner. So this I will call as a rate of rotation of a fluid element. Strictly speaking, I should say average rate of rotation, but many times we do not use average word. We just say rate of rotation, but the significance of average is implicit. Okay. Okay, so I have answered one of our questions. If you remember the first slide, I said rate at which the fluid element is rotating. Okay, I should again say, strictly speaking, the rate at which a fluid element is rotating in average sense, averaged over side AB and AD. Strictly speaking, I should say that, but I will not say that all the time. But this is the question I have answered. I have found an expression for that. This is the expression. And again, this is only the third component. And what would be the SI units of this? If you look at the right-hand side, what is this? Meters per second divided by meter, right? So this is per second. But since there are angles involved and angles do not explicitly appear in derivation, we have to bring them from the context. So from this context, if I write the units of omega 3, I should say it is radian per second, because there was angle involved here, radian per second. Okay. And this is the third component only, which is perpendicular to the plane of motion, a plane in which we are right now considering various things. Now, next, what we want to find is expression for the rate of fractional change in edge lengths. That is the second agenda item. So I want to know, so in this figure at t plus delta t, in general, again, AB will have a length which is different from delta x1, and so same for AD. It will be in general different from delta x2. So I want to know this quantity. I'm not interested in absolute change of length. I am interested in fractional rate of change, and this is how I define fractional rate of fractional change in edge lengths, limiting value delta t going to 0, 1 by delta t. I'm talking about length AB right now. So len means length, just as the shorthand I'm using. So length of AB at t plus delta t minus length of AB at time t, and I will want to divide it by length of AB at time t. So this is the fractional change. By what fraction is the length of AB changing over time delta t? So this is how I will find that. Okay. So to find these expressions, well, length of AB at t is known. It should be delta x1. Right, so this quantity in the numerator, second one, and the third, and the quantity in the denominator, we already know delta x1. What really is required right now to find length AB at t plus delta t, length AB. How do I find it? So I'm going to drop a perpendicular from B to E1 axis, or even to, let me call it horizontal along E1. I drop this perpendicular, and then AM will be what? AB cosine delta alpha. That is the exact expression. But then I will say that cos delta alpha is again almost equal to 1, because delta alpha, I can make it as small as I want, infinitesimal in the limit delta t going to 0, which I will invoke very soon. So I'm working with this assumption that cos delta alpha is approximately 1. It means that AM itself is a good approximation for AB at time t plus delta t. Once I realize that, then I can write length of AB at t plus delta t is length of AM at t plus delta t approximately. And what is length of AM at t plus delta t? It will be one coordinate of B at t plus delta t minus one coordinate of A at t plus delta t, right? The difference between the one coordinates of B and A at this instant, I mean at t plus delta t, will give me length of AM. And then you again go back to the previous slides where we had the full expressions for both the coordinates of B and both the coordinates of A at t plus delta t. I'm just going to borrow the one coordinate of B from that derivation earlier that we did, and one coordinate of A. And when you put that here, it turns out again a couple of terms cancel out, and you are left with this expression. So length of AB at t plus delta t is approximately delta x1, which was its original length. I mean AB's original length at time t, and then an added in an addition, which is del v1 del x1 multiplied by delta x1 and multiplied by delta t. So delta t is also there. Is it dimensionally making sense? So meter per second. So delta x1 will cancel. So we have meter per second multiplied by a time unit, time delta t. So yes, meters. So dimensionally it looks fine. So this is the length of AB at time t, time t plus delta t. Now, if you plug this expression back here, plug this here, this is what you get. Some terms cancel out, and you are left with a very, very simple expression, del v1 del x1. This is the rate of fractional change. Rate in fractional change, no, I should say rate of change of AB fraction wise. I mean, should put the objective properly, but I hope you understand what I mean. Okay. And again, this is derivative is at the location where A was at time t. Okay. So okay, let me just finish the next one also, then I'll stop. Rate of fractional change of edge length AD, if I inquire, rate of fractional change of length AD. Again, I will drop a perpendicular from D to E2 axis and let that point of intersection between these two should be N. Then I can write AN is approximately equal to AD cosine delta beta, AD cosine delta beta. Again, in the limit of delta t being very small, it's a reasonable approximation to set cos delta beta to be 1. So AN can be a good measure of AD at time t plus delta t, right? And then rate of fractional change in length of AD can be written as length of AD at time t plus delta t minus length of AD at t divided by length of AD at t. Length of AD at time t is nothing but delta x2, and then length of AD at time t plus delta t I will approximate as length of AN at t plus delta t, and that can be written as 2 coordinate of D minus 2 coordinate of A at t plus delta t. You put all the expressions in here, and finally you get an expression which is del v2 del x2. This is the rate of fractional change in length AD. Okay, so you see similarity in expression. When you were talking about an edge which was originally parallel to E1 axis, you get del v1 del x1. And now when we are talking about an edge which was originally parallel to E2 axis, you get del v2 del x2. So I stop here, and we'll see if you have any questions. I'll be here for next 10 minutes. Yeah, so a lot of algebra today, and I tried to go slow and tried to explain things, but as I said, your derivation, you doing it is extremely important. Then only you will understand and be sure what was going on. So I'm leaving this slide on the screen. I'll come back and see if you have questions. Okay, it seems there are no questions from your side. Uh, so in next 1 minute, I will end this session. All right, I am ending this session now.